Okay, so in this section, Lecture 4, Part 5, we're going to talk about curve sketching. And of course, this would be the culmination of the work we started way back in Chapter 1, where we're trying to develop a facility for sketching graphs of just about any type of function. And so we're going to culminate our curve sketching skills with like identifying precisely the coordinates of local minimums, local maximums, identifying intervals where functions are concave up, concave down, identifying all the various types of asymptotes that a function can possess, and so forth. Okay, and so at this level, you'll need to recall all of the procedures from chapters 1, 2, and 3 we developed with respect to graphing functions. Okay, so now, applications of differentiation. So, of course, we've been concerned with domain, range, and symmetry. Okay, we've talked extensively about that in Chapter 1. Limits, continuity, and asymptotes. We talked about that in Chapter 2. Remember the discussion of definitions of vertical and horizontal asymptotes in terms of their limits. Talked about derivatives and tangents, Chapters 2 and 3. And we talked about extreme values, intervals of increasing and decreasing concavity, points of inflection, and L'Hopital's rule, which was the most latest discussion. So, so we're going to put all of this together, assemble all of this information together into a comprehensive graph sketching technique. So, yeah, of course, they talk about why not just use a computer. Well, we need a facility for understanding information that's conveyed in graphs, such as how to interpret information. Like, what does it mean for a graph to be concave up, concave down? What is an inflection point? Okay, so we need to understand where these components of curves come from so that we can fit them in the context of some particular, say, engineering or social science or natural science or economics type application. So that's why this is essential. You need to be able to interpret the results. Although the computer is giving you a sketch, what is the information telling you? Okay, so here we have a graph of this polynomial. How did it get there? Okay, so this graph has a This graph appears to have a local maximum and a local minimum, although it's hard to tell. It's not zoomed in properly. Okay, so how do we get all of this information? All right, so yeah, for instance, looking at the graph alone, it would be hard to tell, as this note says, it would be hard to tell that this graph has a local maximum, a local minimum, and of course an inflection point. And that information is useful in some application. Okay, all right, so summary of curve sketching. All right, so guidelines. Okay, so not every rule that we've talked about is essential for graphing a function. Okay, so you don't have to go through the entire suite of steps, only the relevant ones, and that'll become apparent as you begin to analyze the components of the function. So, of course, the domain is essential. You need to know where on the x-axis the graph should be graphed, plotted. Intercepts, of course, x and y intercepts. Okay. Of course, if it's hard to calculate the x-intercepts, like if you have a high-order polynomial, it just may not be possible to calculate the x-intercepts. You may have to use a calculator to do that. Later on in this chapter, though, we will disclose a method for calculating intercepts, x-intercepts of a function, of higher-order polynomials and other types of rational functions. But for now, if it's hard, you may want to defer that technique. And then we talked about even and odd symmetry. Okay, no need to go over that again. Even symmetry, of course, x squared, x to the fourth, absolute value of x, cosine x are examples of even symmetric functions. 1 over x squared, of course, is 1 as well. Odd symmetry, we know that. Symmetric with respect to the origin. And then we have periodic functions, which are typically your trigonometric functions like cosine and sine and tan and cotangent and secant and cosecant. Okay, and so symmetry of periodic functions. All right, so, okay, and then horizontal asymptotes, of course, are found by taking limits as x approaches infinity and seeing if the function converges to a distinctive output. We know how to take vertical asymptotes by taking limits as x approaches some finite number and observing the output going toward plus or minus infinity. We've discussed the details of how to calculate vertical asymptotes. That should be in your Chapter 1 notes. Then we talked about slant asymptotes. Slant asymptotes, we discussed it, okay, because now we've only talked about one type of slant asymptote so far, and that's just by dividing the numerator, the denominator into the numerator and discarding the remainder. Of course, that won't work with trigonometric functions. So we'll see more details on how to calculate different types of slant asymptotes. Intervals of increasing and decreasing, of course, that's found by computing the derivative of the function and assembling a table of signs for the derivative, noting intervals where it's above the where the derivative is above the x-axis, and intervals where the derivative is below the x-axis. Then you can use the first derivative test to analyze where there's points of transition from increasing to decreasing to ascertain local maximums, and use the first derivative test to analyze where the function is transitioning from decreasing to increasing to extract local minimum points. Okay, so very important information. First derivative test, okay. You can use the second derivative test, which is basically an augmented form of the first derivative test. If you find a critical number of the function, and the function is concave up at that critical number, then that critical number is a local minimum. If you find that the second derivative is concave down at a critical number, then that critical number constitutes the abscissa of a local maximum. Okay, and then we talked about concavity and points of inflection. Where the second derivative of a function is greater than 0, it's concave up. Where its second derivative of a function is less than 0, it's concave down, and an inflection point is where the concavity changes direction. Okay, inflection points occur where the direction of concavity changes. All right. Okay, so using all of these details, we're in position now to sketch a graph. Okay, so I guess it's just time for examples. So here's a function from algebra. Let's see how we would sketch 2x squared divided by x squared minus 1. All right, so what do we do? Okay, so we analyze the domain, and clearly the function exists where x is not -1 nor 1. Okay, and this is the interval notation for the domain. The x and y intercepts, okay, are both happen at the point 0, 0. All right, so that's from algebra. The function is even because of this criteria. So the curve is symmetric about the y-axis. All right, so far so good. We can hunt for horizontal asymptotes by taking the limit as x approaches plus or minus infinity. And we see that that limit resolves to 2, so y equals 2 is a horizontal asymptote. Okay, and then we hunt for vertical asymptotes, and we analyze the behavior of the function around vertical asymptotes. So as we approach one from the right, the output shoots to infinity. As we approach one from the left, the output shoots towards negative infinity. So what does that mean? That means that here's 1. Okay, we have a vertical asymptote. As we come at 1 from this direction, we got to go this way. And as we come at 1 from the other direction, we have to go this way. So it's going to behave like this around x equals 1. And the opposite way around x equals -1. So far, nothing new here. Okay, just to rehash. What else? All right, so now we know a preliminary sketch right here. Here are the asymptotes. You have 3 asymptotes. And let's see, we had an intercept, right, at 0, 0. And we know as x approaches -1 from the right, it shoots toward negative infinity. And as x approaches 1 from the left, it shoots toward negative infinity. And so, yeah, and it's even symmetric. Okay, so this is an even symmetric graph. All right, what next? Okay, so now we calculate the derivative using the quotient rule for differentiation. All right, and so I fully expect you to be able to know this. So where is the first derivative greater than 0? When x is less than 0, the numerator is positive. The denominator is always positive. And so it's an increasing function for x greater than 0, a decreasing function for x less than 0. Okay, so that means the function is increasing where x is less than 0 on its domain. Okay, so and it's decreasing for x greater than 0, right? So now you know, and that's probably verified by the asymptotes. Okay. The only critical number, of course, is x equals 0. And since f changes from positive to negative at 0, okay, f of 0 equals to 0 is a local maximum by the first derivative test. Okay, yeah. So the origin is a local maximum. And that's, again, verified by the asymptotes, the vertical asymptotes. All right, so the guy gets bold and calculates the second derivative. And the second derivative is greater, the numerator is greater than 0 for all x. So the second derivative is greater than 0 if and only if x squared minus 1 is greater than 0. Why is that? Because, why is that? Because look at the denominator. The denominator determines the sign of the second derivative, and it's a cube. So if the quantity in parentheses is greater than 0, then the second derivative will be greater than 0. If the quantity in parentheses is less than 0, then the second derivative will be less than 0. So combining these two pieces of information, it's clear that we have an inflection point. Well, not necessarily, because 1 is not in the domain. So there is no inflection point. We just know where it's concave down. So that means, like, for instance, where the second derivative is less than 0, okay, between -1 and 1. Okay, so here's 1, here's -1. Okay, we know that 0, 0 is a local max. And so we basically have to have that branch of the graph right there. It has to be concave down. Okay, and then, so we pretty much have enough information. So if x is outside of -1 to 1, it's got to go like this. Okay, and note that it's increasing here and it's decreasing here. Okay, all right, so that's how you do it. I mean, too bad we couldn't do that in algebra, right? Okay. We should be getting close to being done with this. Yeah, they talk about concavity. Okay, so this is just a carryover from section 4.3. Okay, and so using all the resources, bring them all to bear. There's the graph, okay? So I would expect you to be able to produce this graph without having to use a calculator. All right. Okay, so, here's an interesting one. F of x is equal to x squared over the square root of x plus 1. How do we deal with that? Okay, so the domain, let's see here. All right, so let's carry this along here. Let's see here. Can I copy this? Copy. Slide 50. So let me paste. Let me paste. I'm trying to copy the function. All right, I'll just move it out here. I'll just move it off to the side there and bring it back in. Okay. So take the function. Okay. So looking at the function now, the domain is obviously x plus 1 has to be greater than 0 because we're not admitting complex numbers in this class. All right. So if x plus 1, if x were -1, of course, we'd be dividing by 0. And if x were less than -1, we would have a negative number in the radical, and that's not permitted. So this is the domain. in set notation and using interval notation. The x-intercepts, okay, that happens where the output is 0, and the output at 0 is 0 at x equals 0. Plugging in x equals 0, so the origin is both the x and y intercept. This function will have no symmetry, okay, no symmetry. That's easily verified. All right, so 51. All right, so how about the limit as x approaches infinity? All right, so how do we know this? How do we know this? Well, obviously, we would have to use L'Hopital's rule here. So omitted in step D is L'Hopital's rule. So why don't we take an examination of L'Hopital's rule for this function? So let me bring this down here. And so the question is, the limit as x approaches infinity of f of x. Okay, and so so this is an indeterminate form, right? So this is where L'Hopital's rule comes to the aid. Indeterminate. So this would equal to the limit as x approaches infinity of 2x over 1/2 times x plus 1 to the minus 1/2. Okay. All right, and so that would equal to the limit as x approaches infinity of 2x times 2 times the square root of x plus 1, which that would be infinity. Okay. All right, so it's infinity. Is that what they say? Okay, so that means there's no horizontal asymptote. Okay, all right. That's why. L'Hopital's rule says there's no horizontal asymptote. Okay, and then they talk about as x approaches -1 from the right, okay? So the endpoint of the domain. So what happens then as you do so, the denominator becomes very, very small, and the numerator stays close to 1. And so this limit as x approaches -1 from the right is infinity. So x equals -1 is a vertical asymptote. All right. Okay, so that makes sense. 52. Okay, so here we go and we take the derivative of f of x. Here's f of x for your reference. So it's the derivative of the top, which is 2x, times the bottom, minus the top, times the derivative of the bottom. Here's the derivative of the bottom, all divided by the bottom squared. Okay, and so how do we simplify that? All right, so let me show you how you can simplify that. So just for reference, so down here in the margins, I'll simplify it. So here's the derivative. And so we want to know how this becomes this. So remember the technique which I explained earlier on. When you factor the numerator, you factor on the terms with the smallest power. So in this case, what you want to do is here, we can rewrite the function in terms of powers of the term. So like f prime of x is equal to, replace the radical with its exponential representation. Would be a useful start. Okay, minus x squared times times 1/2 times x plus 1 to the negative 1/2. Okay, and this should be x to the 1/2 power like that, right? Okay, divided by x plus 1. All right, so when you factor the numerator, identify the powers, the smallest powers, and factor on the terms with the smallest power. So the smallest power of x is 1. So factor out an x, and the smallest power of x plus 1 is negative 1/2. So factor out an x plus 1 to the negative 1/2. And then go from there. So this would be times 2 times x plus 1, because x plus 1 times x plus 1 to the negative 1/2 is x plus 1 to the 1/2. All right. Minus, that would be an x times a 1/2. And we factored that out. Okay. All over this. Okay. All right. You see how that works? And then we'll have x times 2x minus 1/2 x, so that would be 2x minus 1/2 x. That would be, what, 3/2 x? Let's see here. 2x, and that would be plus 2. Okay. Divided by, now we send the negative 1/2 power downstairs, so that would be x plus 1 to the 3/2. Okay, now multiply upstairs and downstairs by 2, and so we'll have x times 3x plus 4 divided by 2 times x plus 1 to the 3/2. All right, okay, so that's how they got it. And then that's how they obtained. That's how they got that derivative. Okay. And so what are the critical numbers? Well, the critical numbers, of course, will occur where x equals to 0, and x equals negative 4/3, but that's not in the domain of the function, so negative 4/3 is not. Well, it is a critical number. Negative 4/3 is a critical number, but we don't have to be concerned about it because negative 4/3 is not in the domain of the function. So negative 4/3 is actually not a critical number. Negative 4/3 is not in the domain of the function, although it is a number for which makes the derivative equal to 0, but it's not in the domain. And let's see, x equals negative 1 is not a critical number because we determined that, again, negative 1 is not in the domain. Remember, to be a critical number, the number has to be in the domain of the function, and a critical number occurs where the derivative of the function is either 0 or does not exist. And the number is in the domain of the function. Okay? All right, so just to reiterate that point. Okay. All right, and negative 1 is not a critical number. So 0 is the only critical number. So what do we do with that 0? Okay? Is it a local min? Is it a local max? Is it neither? Who knows? We go on to the next slide to determine. So we know that the first derivative is less than 0. Okay, so let's bring back the formula for the first derivative. For reference, okay, so here's the first derivative. Okay, I'll overlay it right here. So when x is less than 0, or when x is between negative 1 and 0, okay, when x is between negative 1 and 0, exclusive, then this number is less than 0, right? Oh, let's see here. Yeah, the derivative will be less than 0. And when x is greater than 0, of course, all these factors are positive. So no need to compute a table of signs for this. You can pretty much do it by inspection. So that means the first derivative transitions at x equals 0, right? From decreasing, right? It's decreasing here to increasing. So that means x equals 0 must be a local minimum. Okay, that would be the takeaway. X equals 0, a local minimum. X equals 0 is the abscissa of the local minimum point for this graph. Okay, x equals 0 is the abscissa for the local minimum point of this graph. Okay, so we have a local minimum. This is shaping up to be a pretty strange function. Yeah, so there we have the conclusion. Okay. So what about, okay, oh my goodness, they attempt to take the second derivative. Okay, so now, so I'll just move that up here for now. So, okay, so how do they take the second derivative? What do they use that? I guess they use, you want to attempt to calculate the second derivative? Okay. Okay, I guess it would be worthwhile to check the results for the second derivative. So let me erase all of this. So let's calculate the second derivative of this beast. So where is it? Where's my first derivative? Okay. Here's my first derivative, so we'll use this. We'll calculate the second derivative based on that. How do they do it? Oh, use the quotient rule. Oh my goodness. Okay, well, we'll try the quotient rule then. So let's slog through it, guys. So the second derivative is equal to the bottom function times the derivative with respect to x at the top. So that would be, what, 6x? So this is equal to, the numerator is what? 3x squared plus 4x. Okay, as a polynomial. So that would be, its derivative would be 6x plus 4 minus, okay, the top function times the derivative with respect to x to the bottom. And so that would be 2 times 3 halves times x plus 1 to the 1/2, right? All divided by the bottom squared. So that would be 4 times x plus 1 cubed. Right, and so now we just factor on the terms of the smallest exponent. So it appears that we can factor x plus 1 to the 1/2 out. Okay, and so that would be 2 times x plus 1 times 6x plus 4. Okay, minus 3, because the 2's cancel here, right? That'd be 3 times 3x squared plus 4x. Okay, all of that divided by 4 times x plus 1 cubed. Okay, and so we can send this term to the bottom, so that would be, so this would be multiplying, simplifying what's inside of brackets. We would have 2 times, what, 6x squared. I'm using FOIL now. Plus 4x plus 6x plus 4 minus what? 9x squared minus 12x divided by 4 times what, x plus 1 to the 5/2. Okay, and so after further simplification, we'll have 12x squared minus 8x plus 8x, right? Plus 8x. Well, 6 and 4 are 10, so let's simplify that even further. That would be 20x, right? Plus 20x minus plus 8 minus 9x squared minus 12x all over 4 times x plus 1 to the 5 halves. Okay, and so that would equal to 3x squared. Plus 20x minus 4 over 4. I think I may have made a mistake somewhere. Okay, so what did they get? I got an 8x. So I should have gotten an 8x. So why did I not get an 8x? Oh, that's 20x. I forgot the x there. Okay. 20x minus 12x, sorry. Yeah, so now we get what they got. That would be 8x. Okay, so is that what they get? Plus 8. They got a plus 8. Yeah. Plus 8. Okay, yeah, so we agree. So we got the second derivative. So what do we do with it? Okay, we're going to use the second derivative to identify potential inflection points and concavity changes. Okay, so how do they interpret the information? So the denominator is always positive, right? Because we're taking the square root of some number to the 5th, and the domain has already been established to be greater than -1. The numerator is quadratic, which is always positive because its discriminant is -32, which is negative, and the coefficient of x squared is positive. Yeah. Okay, so yeah, so be careful with this. This numerator is a quadratic which has complex roots, but it's pointed up, and the vertex is probably, you'll need to find the vertex of this, but it's probably above the x-axis somewhere. So yeah, clearly you can almost do it by inspection, saying that this quadratic never falls below the x-axis. Okay, so that means that there is no inflection point for this because the second derivative is always positive. There's never any change in concavity. So, but we know that the graph then will always be concave up with no inflection point. Okay, so it's always concave up. Good to know, useful information. So what slide do we bounce to? 56, perhaps 56. Okay, so concave upward on its domain, no point of inflection, 57, slide 57, yep, and there's the graph. Okay, so see how the graph conforms? It's asymptotic with the vertical asymptote -1. You see its restricted domain, it's concave up. Local minimum, we've established that. We've established the limits at infinity, so it's a U-shaped curve. Okay, all right, so you should have no problems with those. I guess I have another example. Okay, sketch the graph of x, e to the x, all right? So the domain is, of course, is a set of real numbers, x and y intercepts are the origin, no symmetry. The limit as x approaches infinity is infinity times infinity, which is infinity. The limit as x approaches -infinity, aha. That is a little bit challenging. Okay, so as x approaches -infinity, we have an indeterminate form. We have an infinity times 0. So probably on the next slide they'll use L'Hopital's rule. Yeah. So they convert the function to a rational function, take the derivative upstairs and downstairs, and they discover that, yeah, so the x-axis, the negative x-axis is a horizontal asymptote. Okay, all right, so good. That utility of L'Hopital's rule is coming into play. Okay, so the first derivative, using the product rule for differentiation, becomes this. This term is always positive, so f prime of x is greater than 0 when x plus 1 is greater than 0, and it's less than 0 when x plus 1 is less than 0. So it's increasing from -1 to infinity, decreasing on negative infinity to -1. So by the IDT, an increasing decreasing test, we know that -1, x equals -1, has to be the abscissa of a local maximum. Okay. So, yeah. So far, based on the information we have, -1, what is the output at -1? So the function is f of x is equal to x e to the x, right? So at -1, the output is roughly a third, right? So at -1, and this would be 1 over e. Let's see, wait a minute. What's the output at -1? No, it would be negative 1/3, so it would have to be here, right? So we call this point -1 over e. So that means, and the negative x-axis, so it's increasing from -1 to infinity. So it's doing that, and it's decreasing. And then we know as x approaches infinity, this thing goes toward increasing. Let's see how we could sketch it with the information given so far. So it's increasing on -1 to infinity, right? And so it has to be increasing, and the output at -1 is down here somewhere. So at x equals 0, the output is 0. Oh, -1. -1 is here. So it's got to go like this. And it's decreasing on -infinity to -1. Okay, so we need probably some concavity action here. So it's decreasing like this. So maybe, and then we know it's asymptotic. So maybe, and let's see, yeah. So maybe something like this. Maybe it has a sharp corner. I don't know. That would be a potential sketch. Concavity, of course, will tell us whether this is a sharp corner or not. So we need to read further. We need more information. Obviously, -1, negative e to the -1 is a local maximum. Okay, interesting graph. I'm curious now. Oh, it's a minimum. F changes from, what was that? Okay, F increasing from, so it's increasing and then decreasing. Oh, wait, hang on. Okay, so it's decreasing, and then increase. Oh, so it's a local minimum. I see now. I misread the information. Yeah, so let's try it again. Let's see what we can anticipate the graph to look like. Okay, so at -1, and then -1 over e, we have to have a local minimum. Yeah, same thing, right? Has to go like that. Yeah, something like that. It would have to have that kind of action. Okay, yeah, so pushing forward, yeah, so x equals -1 is the abscissa of the local minimum. So there's your local minimum calculations. The second derivative is x plus 2 e to the x. So that means x equals -2 has to be an inflection point. So it's concave upward for -2 to infinity. So, and it's concave down for x less than -2. So at -2, -1. So we have this, so it's concave up. So it's got to look like this. It's got to look like that then. Inflection point at x equals -2. Okay, so no sharp corner in IP at x equals -2. And you see how they found the inflection point by noting that at x equals -2, the second derivative changes sign from negative to positive. So to the left of -2, it's concave down. To the right of -2, it's concave up. So it's going to look like this curve now. Okay, so we have all the information now to sketch the graph. Okay, so slide 65. Yeah, so there we go. Yep. Okay. So interesting graph. Another example. Here we go. Sketch the graph of a rational trig function. Something we have never been able to do until today. Okay. All right, so this one looks like it's going to involve a lot of work. Okay, so in the domain, of course, is a set of real numbers because sine and cosine, their domains are on the set of real numbers. And also note that, look at the denominator of the function. Okay, the denominator of the function is never 0 because the sine function never falls below -1. All right, so that's obvious. Okay, the y-intercept, well, let me copy the function. Copy. So let me move it here. Okay, so here's f of x. So the y-intercept occurs where x is 0, and so where x is 0, the output is 1/2. Okay, and the x-intercepts occur where the output is 0, and so the output occurs at 0 when cosine x is 0, and that occurs where at odd multiples of pi has. Okay, so got the intercepts down. So now onward to the rest of the rigmarole. The function is neither even nor odd. Right. I'll leave that to you to check. The function is periodic, okay, because the cosine and sine are both periodic. All right, so here's the interesting notion. Since the function is periodic, we only have to graph a portion of the graph on, say, 0 to 2 pi. And then we'll use a cookie cutter approach to graph the periodic extensions of this function. Okay, so there are no asymptotes because the function exists everywhere, and we can't evaluate infinite limits. It's impossible to find infinite limits for this function. Okay, slide 69. Okay, the first derivative. So let's go through the exercise of calculating the first derivative, and then assessing whether we have any local minimum or maximum points. All right, so let's do that down below. So let me get rid of this. Excuse me. So we're going to calculate the derivative and essentially run the first derivative test of the function. So since it's a quotient, we'll have to use the quotient rule for differentiation. All right, so calculate the derivative of this function. So it will be f prime of x is equal to the bottom function times the derivative with respect to x of the top function, which is minus sine x, minus the top function times the derivative with respect to x of the bottom function, all divided by the bottom function squared. Not sine squared, sorry. 2 plus sine x squared. Okay, like so. Okay, now we'll simplify the numerator. So that would be minus 2 sine x minus 2 sine x minus sine squared x minus cosine squared x over 2 plus sine x quantity squared. Okay, and so that, of course, we can use the Pythagorean identity, so that would be equal to minus 2 sine x minus 1 over 2 plus sine x. Okay, so what are the critical numbers of the first derivative? Well, they happen where minus 2 sine x minus 1 equals to 0. So minus 2 sine x is equal to 1. And so we'll have sine x is equal to minus 1/2. Okay, so where does sine x equal to minus 1/2? Well, that would occur in quadrants 3 and 4, right? Quadrants 3 and 4. And so we know that the reference angle for sine x, we know that the sine of pi thirds radians is equal to 1/2. Okay, so in quadrant 3, we would have the sine of 4 pi over 3 is equal to negative 1/2. And in quadrant 4, we would have the sine of 5 pi over 3 is equal to negative 1/2. Okay, so the critical numbers happen at 4 pi and 5 pi over 3. Is that what they came to the conclusion of? Oh, no, they said, no, it's not pi thirds, it's pi 6, sorry. Pi 6. So we'll make that pi 6, sorry. I got my reference angles backwards. My fundamental angles backwards, okay. Sorry. So this would be, so in quadrant 3, that would be 7 pi over 6. Sine of 7 pi over 6. And in quadrant 4, that would be 11 pi over 6. Oh, shoot. Sorry about that. It went too fast. Okay, so now we're settled. Is that what they get now? Yeah, 11 pi over. Okay. Now, all right. So between 7 pi over 6 and 11 pi over 6, where are you on the unit circle? Okay, let me show you. So here are my coordinate axes. Okay, so between 7 pi over 6, which is right here, and 11 pi over 6 right here. Okay, so if you traverse along this arc, okay, the sine function will be less than or equal to negative 1/2. So on this arc, on this interval between, so if x is between 7 pi over 6, okay, on this interval, f prime of x will be less than 0. Okay, so if you're say between 0 and 7 pi, 0 and 7 pi over 6. Okay, f prime of x f prime of x will be less than negative 1/2. Sorry, not less than 0, but less than negative 1/2. Okay, so if you're from 0 to 7 pi over 6, f prime of x will be greater than negative 1/2. Okay, and if you're from 11 pi over 6, less than x, less than 2 pi, f prime of x will also be greater than negative 1/2. Okay? All right. So now that means we have 7 pi over 6 as being a point of transition. Okay? So at 7 pi over 6, as we approach 7 pi over 6 from the left, okay, what happens to f prime of x? F prime of x is greater than negative 1/2, okay? And when f prime of x is greater than negative 1/2, what does that mean? Okay. Okay, so no, not f prime of x. F prime of, yeah, that's right. F prime of, yeah, so when we should actually say not f prime of x, we should say sine x. Sine x. Change that to sine x. Sine x. Okay, sine x. Sorry, not f prime. Okay. And where's our derivative? So when sine x is greater than negative 1/2, what does that mean for the first derivative? It means the first derivative is what? Greater than 0. Okay, so f prime, see, when we're greater than negative 1/2, say the third, no, when we're less than negative 1/2. When we're less than negative 1/2, negative 5, negative 1/2. Okay, so when we're greater than negative 1/2, f prime of x must be less than 0. Okay, so f prime of x must be less than 0. And then when we're less than negative 1/2, okay, let's see, for less than negative 1/2, say like negative 1, for instance, if sine x equals to negative 1, or negative a third. Let's see here. This is a tricky problem. Let's see, if we're less than negative 1/2, what's less than negative 1/2? Say negative 2/3. Yeah, so, right. So if we're less than, so on this interval, f prime of x will be greater than 0. Okay, so that means that 7 pi over 6 is a point of transition from decreasing to increasing. So 7 pi over 6 must be a local min, perhaps. We'll check. Right? Because as we advance from 0 to 7 pi over 6, we're decreasing, and then from 7 pi over 6 to 11 pi over 6, we're increasing. So, yeah, so that would have to be a local min. And then, okay, so how about 11 pi over 6? We do a transition at 11 pi over 6, right? So 11 pi over 6, as we approach 11 pi over 6, we go from increasing to decreasing. So 11 pi over 6 would have to be a local max, the abscissa of a local max. So 7 pi over 6 is the abscissa of a local min. 11 pi over 6 is the abscissa of a local max, based on our analysis here. So do they reveal that in the next slide, which is what, 57? 70? So let's check. Let's check what their results are. F is increasing on 7 pi to 11 pi. Do we have that? Yep. And decreasing on 0 to 7 pi 6. Yep. And decreasing on 11 pi 6 to 2 pi. Good. So we got the same conclusions. So now they use the increasing decreasing test or the first derivative test to see that the local minimum happens at 7 pi over 6. Okay, and the local max happens at 11 pi over 6. All right, so we came to those conclusions. Now, if you don't know how I got this Q3, Q4 stuff, there is a chart on my trigonometry website which will reveal this information. So the circle of truth, I call it. So you can refer to that, print it out, and use it to answer any potential web assigned questions in this genre of problems. Okay? All right. And you can see me if you need more information about this. Okay. All right, so now we've got the local min, local max from 0 to 2 pi. By the way, you do realize that these abscissas are periodic in 2 pi, right? So we're going to have another local min at 7 pi over 6 plus 2n pi. We're going to have an infinite number of local minimum values. Okay, and we're going to have an infinite number of local maximum abscissas. So actually, the locus of local minimums would be this. And the locus of local maximums would be this. So you have an infinite number. So these are the sets of local mins and sets of local maximums. Okay, all right. Okay, just that's how they came to these conclusions. All right, so next slide, 72. Oh my goodness, they go and calculate the second derivative to check for concavity, right? All right, so let's calculate the second derivative. Okay, so where was my, okay, so using, all right, so we've got this settled. So using our calculation for the first derivative, okay, let's calculate the second derivative. And see where the inflection points are and where it's concave, the intervals of concavity. All right. All right, so we'll start with this function, calculate its derivative. So, okay, so f double prime. Okay, so it would be the bottom function, 2 plus sine x quantity squared times the derivative with respect to x of the top function, which would be minus 2 cosine x, right, minus the top function, which is 2 sine x plus 1, times the derivative with respect to x of the bottom function. So that would be 2 times, I have to use the power rule, times cosine of x, like that, all divided by the bottom squared. So that would be 2 plus sine x to the 4th. Okay, so we can simplify the numerator. So that would be, we can factor 2 plus sine x out and a cosine x out. 2 plus sine x times a cosine x. It looks like we can even factor out a 2. Okay, so that would be 2 plus sine x. Two plus sine x times a negative 1. So we factored out 2 plus, okay, factor out all of this, right? 2 cosine x. And then we would have plus 2 sine x plus 1. Let's see, 2 plus sine x, cosine x 2, 2 plus sine x. Okay, yeah. Divided by, so it doesn't look too painful. assuming I did it right, divided by 2 plus sine x to the fourth. All right, so simplifying what's in brackets, we'll have 2 plus sine x 2 plus sine x times 2 cosine x times what? Negative 2 minus sine x plus sine x. So that'd be negative 2. So we can simplify all that stuff in brackets, right? That would be negative 2. Okay, so that would be negative 2 minus 1 plus sine x. Okay, so let's see here. So let's check what they claim to be the fourth. Oh, okay, so we can send this factor to the bottom. So that would equal to 2 cosine x times negative 1 plus sine x divided by 2 plus sine x cubed. Okay, so now, is that what they got? 2 cosine x times sine x minus 1. Yeah, so that's what, so we got the same thing. Okay. 1 minus sine x, did I get 1 minus sine x? Looks like there's a sign difference. Oh, okay, they have a negative sign out there. And let's see, they also have a 2. So, did I forget my 2? Somewhere I forgot a 2, right? Nope, didn't forget the 2. Okay, so yeah, we got the same answers. Okay, so now, what decides the sign of the second derivative? Well, clearly the denominator is always greater than 0, and 1 minus sine x is greater than 0 for all x, greater than or equal to 0 for all x. So the deciding factor then occurs when cosine x is less than 0, which happens in quadrants 2 and 3 here. Okay, so when x is in this range, the second derivative is less than 0. So we'll have inflection points then at pi halves and 3 pi over 2. Okay, so concave down on this interval and concave up elsewhere. All right, so what slide were we on? 70 something? 72, 73. So it's concave down and concave upward on 0 to pi halves and 3. Okay, inflection points, of course. Oh, and these are the outputs at the inflection points. Okay. Okay, plug in 3 pi over 2. You'll have 0. So here's your function. Okay, 74. Okay, oh, already? So soon? Okay, so here's the graph on one interval. Okay, so okay, there's your graph. And you can see that at x equals 0, output is a half. Okay, there's your y-intercept. Clearly the function output is 0 when cosine x is 0. Okay, so you have the two x-intercepts here. We calculated the local min, the local max. We calculated concavity. It's concave down on pi halves to 3 pi over 2 and concave up elsewhere on 1 pi. Okay, so this is for all intents and purposes one period of the graph. So to sketch the entire graph, the graph on the entire x-axis, we cookie cutter it, right? So let's do that. So let me erase all of this. So we already know, we've already listed all of the local mins and local maxes. Now we know the inflection points, okay, and we know the intercepts. So to the x-intercepts are periodic. So just add multiples of 2 pi to the x-intercepts, multiples of 2 pi to the inflection points, and that's how you can cookie cutter it, okay? So do at least 3 or 4 periods on either side of the y-axis for this graph to be complete, okay? So let's see what we get here. So we take this graph. All right, so copy, paste. So we just take it and we paste it there. Okay. Paste, and you just keep pasting like so. Okay, just paste it together like so. All right, and now all you have to do, okay, all you have to do to determine the periodic extension is just simply add 2 pi, 2n pi to this point. Add, we've already discussed that. Add 2n pi to this point, as well as to here, as well as to here. As here. Okay, so 1, 2, 3, 4. Add 2n pi to these points, and then you'll be set for how to cookie cut the thing along the x-axis. Okay, so not so bad. Okay. All right, so slide 76. Okay, so how about the natural log of 4 minus x squared? All right, so what does that graph look like? Okay, so the domain, obviously for the natural log, oh, let me copy the function, right? 76. Let me copy, won't let me copy. All right, so I'll write it. 77. So y is equal to the natural log of 4 minus x squared. Okay, well obviously 4 minus x squared has to be greater than 0 for this to work. And in set notation, this will be the set x such that x squared is less than 4. And so you can take the square roots of both sides. So the absolute value of x is less than 2. So this is the domain of the function, -2 to 2. So your graph is going to be confined to this interval and nowhere else. Okay, so you have a very small domain for this function. All right, slide 78. Okay, so the y-intercept occurs where the output is 0. Okay, so substitute x equals 0. No, the y-intercept occurs where the input is 0, I beg your pardon. So y is equal to the natural log of 4 minus x squared, plug in x equals 0, and you'll get the y-intercept. To get the x-intercept, set the function equal to 0 and solve. So 4 minus x squared has to equal to 1, so x squared equals to 3. And the x-intercepts happen at plus or minus square root of 3. So is that within our domain? Are both of those numbers within our domain? Yes, because the square root of 3 is 1.7, and the negative square root of 3 is greater than -2. So yeah, so we have 2 x-intercepts and a y-intercept. All right, 79. So the function has even symmetry. How do we know that? Let's check. Well, because of the x squared term, an even function. So if you plug in a negative number for x, it's the same as the positive number. Okay, so yeah, so even symmetry. So the curve is symmetric about the y-axis. So far what we've seen is this. Okay, so we have something like this, right? That's a +2. So we have an x-intercept at negative square root of 3, an x-intercept at the square root of 3, And at x equals 0, we'll have the natural log of 4. And we got something that looks like this. Okay, so that's, but it remains to be determined what the concavity is. Okay, but I suspect the graph will look like this. So we have even symmetry, but we need to prove this further. We need to prove that that will be the graph. So slide 80. Look for vertical asymptotes at the endpoints of the domain. Okay, so 4 minus x squared approaches 0 from the right as x approaches 2 from the left. Yep, and as x approaches 2 from the right, we have, okay, so we have these two limits, yeah. So in either case, the output goes to negative infinity as x approaches 2 from the left, or x approaches negative 2 from the right. So the lines x equals 2 and x equals negative 2 are vertical asymptotes. Okay. All right. So this is from algebra, basically. All right, so there's the derivative. Remember, how do we got this? Okay, so the function was the natural log of 4 minus x squared, and you remember how to take the derivative of a natural log function. So f prime is equal to the derivative of the function, which is minus 2x, divided by the function itself. Okay, and there it is. And so we examine where it's greater than 0 and less than 0. And so on the function's domain, of course, so f prime of x is greater than 0 when the numerator is greater than 0. Okay, because the denominator is always greater than 0 on the domain. So when x is negative, f prime of x is greater than 0. And when f prime of x is less than 0, when x is positive. So x equals 0 is a transition from an increasing to a decreasing function. So x equals 0 has to be a local maximum. All right? Slide 82. So x equals 0, of course, is a critical number. F changes from positive to negative at 0, so f0 equals natural log of 4 is a local maximum. Apply the first derivative test. What is this? Oh, I skipped. No, I should be. It jumped a slide. Sorry. 83, right? Okay. Yeah, let's see. 82. Slide 82 was it? Okay, so slide 83. Okay, so slide 83. I'm trying to get to slide. Okay. Okay, so we had the first derivative. Okay, so now slide 83. I need to be on slide 83. Sorry. All right, so here's the calculation of the second derivative, and I'll leave that to you to calculate. It's pretty straightforward. So looking at the second derivative, it appears to be less than 0 for all 0. So the curve is concave down on its domain, no inflection point. Okay, so that's why you calculate the second derivative. All right, so slide 84. We're ready to sketch, right? Yep, and there it is. Okay, so we have the intercepts. 3 intercepts, a local max, symmetric with respect to the y-axis, vertical asymptotes, concave down. Anything else? Okay, so there's the graph. All right, so now we can talk about slant asymptotes. Slide 85. Some curves have asymptotes that are oblique. Okay, slant. Oblique means slant. Okay, so why does it keep jumping? I'm sorry, I apologize for the jumpingness of the slides. Okay, so what slant asymptotes can be interpreted as, if the limit as x approaches infinity of a function shown in blue minus, say, some line is equal to 0, then the line is called a slant asymptote. Okay? And they note this is because the vertical distance between the curve f of x and the line approaches 0 as x approaches infinity, and we could have a similar situation as x approaches minus infinity. Okay, so we've seen that. First project, there's a prime example. And we've also talked about this. For rational functions, slant asymptotes occur when the degree of the numerator is more than the degree of the denominator. And then they suggest using long division, as did I. But you can use synthetic division if you want. Okay, and so, okay, I think, well, okay, this is essentially a rehash of project 1 right here. So x cubed over x squared plus 1. Obviously, it's going to have a slant asymptote. All right, so is there anything revealing? Domain, xy intercepts. It's an odd symmetric function. What else? No verticals. Limits as x approaches infinity. Are y'all getting tired of this? Okay. So actually, they did it rather ugly, a rather ugly way of calculating the slant asymptote. I typically suggest doing a long division. Okay, you may use synthetic division. Long division seems more intuitive. Okay, and so you discard the remainder, and so x, the line y equals x, is a slant asymptote. It's easier than all of this rigmarole calculations. Okay, what next? Slide 92. Well, they calculate the first derivative. Okay, you can do that. I'll leave that to you to do. The first derivative is greater than 0 for all x. Okay, well, the denominator is always greater than 0, and yeah. So the derivative, first derivative is greater than 0 for all x, except, of course, x equals 0. So this is an increasing function, so it's forever increasing. So there are no local minimums or maximums for this curve. Okay? No changes in signage. Yeah, note carefully this point. No changes in signage. Okay? You need to have a change in sign for a transition point for a local min or local max. Okay. Oh, they calculate the second derivative. Good Lord. Okay. Well, anyway, there it is. So the second derivative is equal to 0 when x is 0 or x is plus or minus the square root of 3. So okay, so they build this table of signs. All right, so let's calculate the table of signs for the second. Okay, so let's just run with this. Let's just run for this and calculate where the intervals of concavity are and what the inflection points are. This would be a good time to review the table of signs. So let's take this work right here. Now we'll use this. Okay, so remember the table of signs. Okay, so we write table of signs for the second derivative. So we'll have 2x. We'll have, well, x squared plus 1 cubed is always positive, so no need to include it, right? It has no bearing on the table of signs. 3 minus x squared. So that would be the square root of 3 plus x times the square root of 3 minus x, right? So we have 3 factors that determine the fate of the second derivative. And they happen at negative square root of 3, 0, and the square root of 3. All of these numbers are in the domain. Okay, so if x is positive, 2x is positive. If x is negative, 2x is negative. So if x is greater than negative square root of 3, this factor is positive. If x is less than negative square root of 3, this factor is positive. If x is greater than, that factor is, if x is greater than negative square root of 3, if x is greater than negative derivative 3, it's negative, right? It's positive here. Okay. All right, so that means on this interval, the second derivative is positive, negative, positive, negative. Okay, so we have inflection points. So it's concave up here, concave down here, concave up here, concave down there. So x equals -3, abscissa of an inflection point. X equals 0, abscissa of an inflection point. X equals square root of 3, abscissa of an inflection point. So it looks like this thing's going to have 3 inflection points. Let's read on. 3 inflection points. Wow, that curve is really a serpent. 95. Okay, so there's an assessment. So they say concave down, concave up, concave down, concave up. Yep, just like we concluded. So 96 must bring it all together. Okay. So yeah, so here's the graph. No local mins, local maxes. There's your slant asymptote. There's your x-intercept as well as an inflection point. So you have 3 inflection points right there. So concave up. So I'll accentuate in blue where it's concave up. Concave up. Concave up. Concave, and I'll accentuate in green where it's concave down. Concave down. Concave down. Like so. Okay. So the inflection points determines the shape, the waviness of the graph. All right, so that's it for graphing. Now, I want to show y'all something. I believe on the class website, there are some additional graphing problems that I have solutions worked out for. So let's investigate that. I can't remember offhand, but we'll check. So let's go to the class website. And I believe I have some homework solutions. Yeah, previous homework assignments. Can I use this? So let's check. Maybe somewhere around 24 or so. Let's check homework 22. Loading, huh? I'm not sure if it's going to resolve. Yeah, okay, so I can't get the web filter to work on this. So check one of these homework assignments. I believe I have some more complicated graphs from section 4.5 of the text. So go through these and see which one of these homework assignments maps to section 4.5, and the solutions are posted. So some additional graphing techniques are present there that are kind of interesting. I believe in one of them I actually used the cosine function as a slant asymptote for a rather unusual function, so you might want to look at that as well. So if you have any questions about these previous homework assignments, come see me. They contain some much broader based details. Okay, so that would conclude our lecture for section 4.5, graphing functions.